Okay, so this is just a real brief overview of eigenvectors and eigenvalues. If you're comfortable with this topic, uh, you don't have to watch this. This is more for people who haven't had linear algebra in a while. And again, you're not going to be calculating a lot of eigenvectors and eigenvalues by hand, but for the homework and for the exams, you should be able to do it on a calculator or something pretty quickly. So remember lecture 0, I said if we start out with the set of all possible unit vectors in a circle, and I apply some linear transformation to them, given by matrix A or tensor A, the most they can become is an ellipse. Right? Now, when this happens, most vectors are going to change direction. You can imagine if I start with the vector that goes along the x-axis and I stretch my circle out along 45 degrees, this vector is going to get longer, but it's also going to change its angle. Right? But there are, in 2D, this transformation, there are two vectors, special vectors that don't change their direction, and they're called the eigenvectors. Right? One is located along my stretching direction. The other one's going to be orthogonal to my stretching direction. This vector is going to get longer. This one's going to shrink. Right? The major and minor axes of my ellipse are going to change length, but they're not going to change directions. And the directions are eigenvectors. C-T-O-R-E-R, vectors. And the scaling, how much they grow or shrink, or are eigenvalues. So what we're looking for, if we have our stress as an example of a second-rank tensor, right? That's our traction. So we're looking for our this is our stress equation. Sigma normal equals our traction vector. We're looking for where our traction vector equals some scaling of our normal vector. Like that. All right? So we can bring this back over on the other side. Right? We can write this as sigma minus lambda I n equals 0. Or in terms of indicial notation, right, as sigma ij minus lambda delta ij times nj equals 0. And that's a set of 3 equations, right? So we're looking for the solution of this set of linear equations. right? 3 equations, and there are, in this case, 3 possible values for lambda where this will work in 3D, right? Because stress is a symmetric and positive definite tensor, we're guaranteed to have real eigenvalues, which is also very nice. Okay, so how do we find these values of lambda, these eigenvalues, and then from there, how do we find the eigenvectors? Well, let's go back to our system of linear equations, sigma minus lambda I n equals 0. Remember that systems of linear equations like this have a solution if and only if the determinant of A equals 0. If you don't remember that from linear algebra, learn it now. So, what this tells us is that this system only has solutions if the determinant of sigma minus lambda I equals to 0. So we're looking for the values of lambda that make this determinant equal to 0. Okay? Now, if you remember your linear algebra, right, we can use the Leibniz method for calculating the determinants, and what we end up with is polynomial expansion. Right? Like this, and that gives us, we get the characteristic polynomial. Right? Where these are the invariants of our tensor. Right? This is the trace. This is that 1/2 trace of sigma squared minus the trace of sigma squared. And this is the determinant of sigma. But we'll come back to that in a minute. So this is just a little linear algebra theory. But refresh yourself on how to take the determinant of a 3x3 matrix. Right? 2x2 is easy, right? Right? It's just AD minus BC. Right? 3x3 right? You block out one row and one column, right? So we do this expansion, right? So we'll go down this row and this column here, so that becomes A times the determinant of this 2x2 matrix, E I minus FH minus, we have to decide whether we want to go across or down. Let's go down D, so that blocks off this and this, times the determinant of the resulting, so that becomes BI minus CH plus G times BF minus CE. So if you don't remember how to take the determinant of a 3 by 3 matrix, look it up. Go to Wikipedia. It's helpful. So let's go through a eigenvalue problem for a 3 by 3 for a 3D stress, and we'll make it as easy as possible. So let's take this stress tensor. Okay, symmetric. From inspection, those of you who remember your linear algebra, you know that 2 has to be an eigenvalue and 100 is an eigenvector. But in case you don't remember that, let's go through it. Right, so what we want to do is set up the determinant of sigma minus lambda I is equal to the determinant of 2 minus lambda, 0, 0, 0, 3 minus lambda, 4, 0, 4, 9 minus lambda. All right? And the determinant of this is going to be 2 minus lambda times 3 minus lambda, 9 minus lambda, minus 16. That equals 0. So let's expand this out. This gives us 27 minus 3 lambda minus 9 lambda plus lambda squared minus 16. And that gives us lambda squared minus 12 lambda plus 11 times 2 minus lambda equals 0. And we're left with minus lambda cubed. I'm not going to show the algebra. Plus 14 lambda squared minus 35 lambda plus 22 equals 0. So this is our characteristic polynomial. And let's check this out, right? So before we said it has to have the form of lambda cubed plus I lambda plus 2 lambda plus the third invariant. So let's check this. So the trace of our original matrix, 2 plus 3 plus 9, that's 14. Good. What about our second invariant? Well, let's see. So the trace of sigma is 14. 14 squared. So we have the trace of sigma squared minus the trace of sigma squared. So the trace of sigma is 14. 14 squared is 196. Sigma squared, I'm not going to work it out here, but is 48, 0, 48, 97. The trace of this is 126. 196 minus 126 is 70. 1/2 of 70 is 35. That's good. And the determinant of this is 2 times 3 times 9 minus, which is 2 times 27 minus 16, which does give us 22. Right? So our invariants work. Okay, so now we want to solve this polynomial for the zeros. So I only multiplied it out like this because I wanted to show the relationship with the characteristic polynomial and the invariance of the stress tensor. But we go back up here, 2 is already factored out. So we know that lambda equals 2 is 1, and the other eigenvalues are 1 and 11. The zeros of this polynomial here, right, by inspection, you can factor that as lambda equals 1 and lambda equals 11. That's going to be B0. So now that we found the eigenvalues, now we need to find the eigenvectors. Right? So, how do we do that? Well, let's plug it back into our system of linear equations, right? We have sigma minus lambda I times n equals 0. So let's plug our values of lambda into this and then solve for n. Easy peasy. So for lambda equals 2, that gives us 0, 0, 0, 0, 0, 1, 4, 4, 7, n1, n2, n3 equals 0. Well, 0, n1 plus 0, n2 plus 0, n3 equals 0. That's trivial, right? N2 plus 4n3 equals 0, and 4n2 plus 7n3 equals 0. And the ratios here aren't the same, so the only solution this has is if, well, we can just work it out real fast, right? So n2 equals minus 4n3. So if we plug that in, 4 times minus 4n3 plus 7n3 equals 0. Right, that tells me minus 16n3 plus 7n3 equals 0, or minus 9n3 equals 0. Right? Obviously, that only works if n3 is 0. Do the same thing and get n2 is 0. So that means n1 can take any arbitrary value. So we want to keep things unit vectors, so that's 1. Okay, what about, let me erase all this here. What about our other eigenvectors? So for lambda equals 1, right? What do we have here? We now have 1, 0, 0, 0, 2, 4, 0, 4, 8, right, times n1, n2, n3 equals 0, 0, 0. All right. So let's multiply this out. n1 equals 0. That's easy enough. And the other two, we have 2n2 plus 4n3 equals 0. 2n2 plus 4n3 equals 0. And 4n2 plus 8n3 equals 0. Okay, so this is good. So our ratio is the same. So we know that n2 and n3 are not equal to 0. So we have 2n2 equals minus 4n3. n2 equals minus 2n3, right? Which gives us a vector of 0, 2, minus 1, right? And we want a unit vector of that. So 0, 2 over the square root of 5 minus 1 over the square root of 5 is the eigenvector. And then if you work through it for lambda equals 11, you'll end up with 0, 1 over the square root of 5, 2 over the square root of 5 as your eigenvectors. Okay, so for class, I want you to be proficient with using your calculator or your computer or whatever, however you want to do it, with finding the eigenvectors and the eigenvalues. If on the exam, right, most of the time you're going to end up with a matrix that looks like this, right, where I've got these. So you can know one of the eigenvalues by inspection. So that means even if you have to do it by hand, you're only factoring a quadratic polynomial, not a cubic, right? So you should be able to factor quadratics pretty fast. So hope that struck a chord in memory. If not, you'll have plenty of time to practice it on the homework. Okay.